now and slamming on brakes, but it takes a long distance to stop. I've seen you guys drive, you get some tailgaters and you're on the phone while you're doing it. Quit that. Sound good? Okay, so we're going to now look at taking a graph, positive function, and we're going to look at ways to find the area underneath that graph. Now, if the graph is a nice straight line, I can find the area by looking at area of a triangle or a trapezoid. That's real easy. But if the graph is some curvy function and I want to find its area, then I've got to kind of break it up into shapes that I know and love. And the easiest shape that we're going to work with is going to be a rectangle. Right? I can break it up in any shape I want, but I'm going to start by breaking it up into rectangles. So that's what we're going to do in section 5.2. Let's see how these go in order. That way, I better number these. We're going to look at the area under a curve. And we're going to do it by approximating it, and we're going to do it by exacting it using the calculus limit. So let's start with some kind of easy function. Let's draw the graph of, say, y is equal to x squared plus 1. What does a graph of y is equal to x squared plus 1 look like? It's a parabola, right? Draw your parabola with a vertex at 0, 1. So let's find the area beneath the graph of y is equal to x squared plus 1 above the x-axis between the vertical lines, say x is -1 and x is 3. Let's make a pretty big graph here. Zoom out a little bit. I can make a big enough graph for you. We'll find a pencil so it looks like it has lead. All right. That's a parabola. When x is 0, y is 1. When x is -1, y is 2. And when x is 3, y is 10. So I'm going to have to fake my scale a little bit here and say that this is the point 3, 10. And then we'll draw this parabola through there. Like that. Now put in the two vertical lines, x is -1 and x is equal to 3. So there's all kinds of ways that we can find this area. I can look at maybe inscribing this little rectangle in there, and I can find the area of this rectangle, and then approximate these with little triangles and little triangles, and get a rough idea of what the area is. But I want to make it my approach not per graph. I want to make my approach for any function in the world. So I'm not going to chop it up based upon the shape of this function. I'm going to take it in general for any function in the world y is equal to f of x above the x-axis from x is equal to a to x is equal to b. Here's my plan. I'm going to take the interval from a to b and I'm going to cut it up into equal sized subintervals. Maybe I'll cut it into 2 subintervals, go right to the midpoint. Then I'm going to take these 2 segments and make rectangles out of them. But I'm going to be uniform. I'm either going to use the left endpoint to draw me the height or the right endpoint to draw me the height. If I use a left endpoint, my rectangle for this example looks like this. And then the next rectangle would look like that. And then I can find the area of this. This is the midpoint here. I can take this length times that height. And that height is going to be f at a. Then I can take this length times that height, and that's going to be f at the midpoint to give that height. I'm off by a little bit because there's a little bit hanging out here, here, and here, but I don't care. I'm just approximating the area so far. So first I'm going to approximate it. I'm going to approximate this area by inscribing or circumscribing, or both, by rectangles, whose height is given by either the left endpoint or the right endpoint of each subinterval. That'll be called a left sum, or the right endpoint, which will be called a right sum. In my general example, I just drew you 2 rectangles, and I was off a little bit. The idea is if we put more rectangles in here, we might get a better approximation. We put more and more rectangles in here. Eventually, we'll fill this thing up with a bunch of rectangles. If I have that many in here and go from the right endpoint over, I'm getting closer to the actual area. Very little is hanging above. We put more and more and more and more and more rectangles in there until eventually the rectangle base width is infinitely small, and I'm just coloring this in with essentially vertical lines, and I'll get the entire area. Takes a while to do that. Let's approximate this area of in our example with 4 rectangles, and let's compute a left sum and then a right sum. So in our example, let's approximate the actual area with 4 rectangles, 4 equally spaced, and in part A, use a left sum and in B, use a right sum. I choose 4 rectangles because that's how long this interval is from -1 to 3. That means I can put my subdivision lines at all the integer values. So look back up here in this picture. I'd have a vertical line at x is 0, a vertical line at x is 1, and then another one at x is 2. And so I'm going to have 1, 2, 3, 4 rectangles. In part A, it's a left sum. So in rectangle 1, I'm going to take the left endpoint as its height. And I'm going to find the area of this rectangle. And then in rectangle number 2, I'm going to come straight across from here and find the area of that rectangle. And then in number 3, I'm coming across from the left endpoint here, and I'm going to get the area there. And then in number 4, I'm going to do this. So I get too much area here, but I leave gaps there. That looks like a pretty nice little balance. Maybe I'll be close to the actual area with those 4 rectangles. How wide are each of these bases? Well, I picked it so they all be 1 unit wide. I'm going to call the width of the bases delta x. In general, if I have the interval from A to B, and I want to make n partitions, n subdivisions of the interval from A to B, and I want them all to be the same size, then I find out how wide that interval is, and I cut it up into n equal pieces. And that'll give me my delta x term. So in general, with n rectangles, my delta x is going to be how wide the interval is, b minus a, cut up into n equal pieces. That's going to be the base width of each of our rectangles. Then the height depends on the y value at the particular endpoint in discussion. In our picture, I need to find the y value when x is -1, and then multiply it by the width of that rectangle. Then the y value when x is 0 times the width. Then when x is 1 times the width, and when x is 2 times the width. So in our example, we have that our area is roughly equal to f of -1 times our delta x plus f of 0 times our delta x plus f of 1 times delta x. And now this next rectangle has its height, f of 2. All of our delta x's are 1. To get those y values, I just go back into the equation and I plug them in for x. So f of -1 is already marked as 2. F of 0 is 1. F of 1 is also 2, so my picture is real bad scale. So we're plugging them into this, x squared plus 1. So f of 1 was 2, and delta x is 1. F of 0 is 1. F of 1 is also 2. And f of 2 is 4 plus 1 is 5. And so my approximate area is 5 plus another 5, roughly 10 square units. Remember, that was our left sum. So that's part A. In part B, we make a right sum. So let me redraw this picture so that I don't have to keep moving my paper. In part B, that's a bit slow. Let me move it up a bit. There's 1. Still can't get my scale right, something like that. So that was 310. Let's see, -1, 0, 1, 2, 3. So my 4 rectangles again. The first one, when I have a right sum, finds me the area here. The second one, remember this had to be at 2, but can't see that, finds me the area there. Third one gives us this much area. And then the fourth one gives us that much area. And so for the right sum, just that our area, the height is given by the right endpoint. So my first subinterval contains the interval from -1 to 0. So the right endpoint has as its height f of 0. The width of the rectangle is delta x. The next interval goes from 0 to 1. So f of 1 is that height on the right. F of 1 times delta x. Then I have to add f of 2 times delta x. And then finally f of 3 times delta x. All of the delta x's are 1. F of 0 is 1. F of 1 is 2. F of 2 is 5. And f of 3 was 10. So I have 15, 16, 17, 18 square units. So those are pretty crude. That's a big jump in area. Somewhere the actual area is a number between 10 and 18. If I want to get better at approximating this, I increase the number of rectangles. I've got 4 rectangles in here. Let's increase the number of rectangles to 8. Let's subdivide every subdivision. So to get a better approximation of the area, let's use 8 rectangles. So take the interval from 0 to 1, I'm sorry, from -1 to 3, partition that interval up into 8 rectangles. So I had 4 in there. So that was at 0, 1, 2. So to get 8 rectangles, I'd have to be here at -1/2, +1/2, 3/2, and then 5/2. I've got that curve in here, right? The curve is in here somewhere. Not drawn to scale. Yeah, it's way up there. So now what is delta x? How wide is each base? Are they still out there? Cut my boxes in half. So all of my delta x's are going to be 1/2. In part A, we did a left sum. So for the left sum, I need that height, that one, that one, that one, that one, that one, and that one. So my left endpoints are going to be -1, -1/2, 0, 1/2, 1, 3/2, 2, and 5/2. And my left sum would look something like this. I'm going to have f of -1 times delta x. Let me factor out the delta x way out at the end. So then f of -1/2, and then f of 0, then f of positive 1/2, then f of 1, f of 3/2, f of 2, f of 5/2, and that's the last rectangle. 3 would be the right endpoint. So I stop there, then I multiply by delta x. So I should have 8 rectangles, 1, 2, 3, 4, 5, 6, 7, 8. The f's give the height, the delta x gives the width. Height times width is the area of each rectangle. To get those y values, again, we're plugging them back into x squared plus 1. So here we go. -1 squared plus 1 is 2. -1/2 squared is a 4th. 1/4 plus 1 is 5/4. 0 squared plus 1 is 1. 1/2 squared plus 1 is another 5/4. 1 squared plus 1 is 2. 3/2 squared plus 1 is 9/4, plus 4/4 is 13/4. 2 squared plus 1 is 5, and 5/2 squared is 25/4, plus 4/4 is 29/4, times delta x, which was 1/2. So it doesn't fit, times 1/2. Right up in here. All right, fun with numbers. Let's see, 5/4 is 10/4, plus 29 is 39/4. That's 49/4, plus 3 more is 52/4. 2, 3, 5, 10, plus 10. Let's see, 4 goes into 52. How many times? 13 times, so that's even. 13 plus 10 is 23. So we get 23 divided by 2, which is 11.5 square units. All right, let's do a right sum. So now in each interval, like between -1 and -1/2, my right endpoint is going to be f of -1/2. Between -1/2 and 0, the endpoint on the right is f of 0. So always use the right number. Then we'll have f of 1/2 plus f of 1 plus f of 3/2 plus f of 2 plus f of 5/2. And then the last right endpoint is f of 3. And then multiply that by the width of each rectangle. Since it was a common factor, I pulled it out. Count them, make sure we have 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. We figured out all of these numbers above except for f of 3. So let me pick these numbers out from above. F of -1/2 was the 5/4 plus 1 plus another 5/4 plus 2 plus 13/4 plus 5 plus 29/4. And now I plug in the 3. 3 squared plus 1 gives me 10 times delta x. When I added up all those fourths up here, I got 54/4. Let me double check my arithmetic. 29 plus 13 is 42, 52/4. So I still have that. Now let me add my whole numbers up. 1, 3, 8 plus 10 is 18. Delta x was a half. 52/4 was 13. 13 plus 18 is 31. So I get 31 halves, which is 15.5. So I narrowed it down that the actual area is some number between 15.5 and 11.5. That's still a big gap. So what anybody with any sense would do would be put more rectangles in there. The easiest way to do it is double up the number of rectangles. Go from 4 to 8, 8 to 16. Now, if you wouldn't do this by hand, I'd probably do it on a little computer. These TI calculators do it for you. You just put the number of rectangles in there and it runs a little program to find a left sum and a right sum. And you can do this over and over and over again until these two numbers are really, really close to each other. And then you can say the actual area is bounded by a certain number. But that ain't no fun, crunching numbers. Everything that I did here, I can do symbolically. I don't need the numbers. And I can put more rectangles in here, infinitely many, by using a limit. And that's what we're going to do next. We're going to define something called a Riemann sum. This is an example of a Riemann sum, a left sum and a right sum, but we're going to do it in general. Instead of having the actual coordinate of the left endpoint, I'm just going to keep adding an increment in x to the endpoints. And then instead of plugging in a number, I'm going to plug an expression in there that involves the increment in x. Then I'm going to let the number of rectangles go to infinity so that we eventually are coloring in straight lines. And I'll do it for this particular example. So here's the general thing. Oh, I have no more paper. Class is over, no more paper. That was like several pieces of real paper. Two pieces. Class is stayed. You thought you were going to read. Oh, nice, dirty looking. Okay, so the idea is keep sticking in more and more rectangles by subdividing the interval from A to B with smaller and smaller values of delta x. Remember that delta x was equal and is the number of subdivisions. And so we're going to do this. This should get us closer to the actual area. All right, so let's see. Take an interval from A to B. Suppose you got a graph up here. Here's my interval from A to B. I compute my delta x by taking b minus a divided by n, and I move over delta x units. So my first endpoint here is going to be a plus delta x. Then I move over delta x more. So my second endpoint will be a plus 2 times delta x. Move over again. The third endpoint will be at a plus 3 delta x. Is that a delta? I can't see. And on and on and on. So I'm here at the kth endpoint, and I'm at a plus k times delta x. And I keep going on and on and on until I'm at the right one. But if I'm doing a left sum, then I just find the y value here, f of 0. I'm sorry, f of a plus delta x plus f of a plus 2 delta x plus f of a plus whatever delta x, and I form those sums. So for a left sum, we'd have f at a times delta x to give us the height times the width. Again, I'm going to factor out the delta x. Plus the next one, the next left endpoint is here, f at a plus 1 times delta x plus f at a plus 2 delta x, so on until I'm at the kth one, and so on until I'm at the one right here, right before the b. So that'd be n minus 1 moved over from there. And then I take all of that and I multiply it by delta x. Get up there, Paige. So a plus 1 delta x, a plus 2 delta x, blah, blah, blah. Kth one has a plus k delta x. Keep going until we're at this endpoint right here. B minus delta x, or n minus 1 times delta x. This sum can be written succinctly using this notation. This Greek letter, capital sigma, when used in math, denotes the sum of. We're going to make the sum of all of the f values. And so the general one is the kth one, f at a plus k times delta x. Then we're going to multiply them by the heights. And we're going to do this, say, from k is equal to, so my first one didn't have a k in it, so I'm going to go from 0, and I'm going to go out to this one, to n minus 1. This is called sum of heights times widths. Then I said we're going to put an infinite number in here. So we're going to take this counter here, which is b minus a over n. I'm going to change my k's. I'm going to go from 1 to n. It shouldn't make any difference. That would give me right endpoints anyway. And then we'll have f at a plus k times delta x. Delta x, we said, was b minus a over n. And then multiply by delta x, which is b minus a divided by n. We want to make this an infinite number of rectangles, so we're going to put a limit up here. We're going to take the limit as the number of rectangles goes to infinity. And this will give us the actual area, not approximately the area. This gives the exact area. So when I shifted this over 1 unit, then it takes this over 1 unit, and this becomes the right sum. Doesn't matter. If I'm going to have an infinite number of rectangles, my left sum and my right sum are all going to be squished together. Taking n to infinity makes the width of each rectangle infinitely small, so that it's essentially a line segment. And it runs this to infinity. So it makes the delta x go to 0 as the number of rectangles goes to infinity. This is called a Riemann sum. The limit of that Riemann sum is defined as the area under the curve. And we're going to do it. I'm going to have to pull out some formulas for you eventually. I'm going to do it for the example that we just started with, the x squared plus 1. That's my plan. So back to our example. And the interval flows from -1 to 3. Okay, so we compute n subdivisions of that interval gives the width of each subdivision as 3 minus -1 over n. That was my b minus a over n. So that simplifies to 4 divided by n. I'm going to use this up here where my counter begins at 1 so that I'll have a right sum. My left endpoint is -1. And so for a right sum, my plan is to compute the sum of f at the a in our example is -1. Then I'm going to have k multiples of my delta x. Delta x is 4 over n. That's always at the right endpoint, each subinterval. And that's the height times the width. And I'm going to do this from k is equal to 1 to n. So I got to take this number, or expression anyway, plug it in for x to get me the f of that. So it would look like the sum from k is equal to 1 to n. I put -1 plus 4k over n in for x. So there's the x squared plus 1, and this goes in here. Let me write that as 4k over n squared plus 1. Then I multiply that by delta x, which is 4 over n. Are you with me? That's the height times the width. So instead of plugging those numbers in one at a time, I just plug in the formula for computing those numbers. Now I'm going to simplify that. I'm going to square this thing here, and then add the 1, and then multiply by that. So let's see, when I square that, I get the first term squared. -1 squared is just 1. Then I'm getting twice this product. -1 times 4k over n, done twice, gives me a -8k over n. And then I get the last term squared, which will be 16k squared over n squared. And then I have that plus 1. And then I'm multiplying through by 4 over n. Squared this out. Then I'm going to add the 1, and then I'm going to multiply by 4 over n. So let's put these two together and get a 2. And then send through the 4 over n. So 2 times 4 over n gives me 8 divided by n. Then 4 times 8k over n with the minus sign will give me -32k over n squared. And then 4 times 16 gives me 64k squared over n cubed. Good to there? Now I'm adding things up that look like that, where my counter depends on K. If I have a whole list of numbers to add up, it doesn't matter if I add up the first three and then the next one, the next one. I can add up all of these and all of those and all of those. In other words, I'm going to add like this. I'm going to distribute the summation symbol through here. Okay. K is the counter. This doesn't even have a counter in it. This has the counter in here and here. These have nothing to do with that. So these will become common factors. So I'm going to pull them out and rewrite this sum like this. I'm going to pull this out here so that this first sum would have an 8 divided by n. And then the sum from K is equal to 1 to infinity. Now this factor in here is a 1. I'm going to pull out the 32 over n squared. And then I'm going to have the sum from K is equal to 1 to n of K. And then I'm going to pull out the 64 over n cubed. K squared. And I don't need to put infinity up here. This is an n up there. We can figure out these three expressions in terms of K. Actually, we can figure out those three expressions in terms of n. Suppose n is 5. This says I'm adding 1 to itself 5 times. 1 plus 1 plus 1 plus 1 plus 1. I got to get 5. Oh, you guys want to go? Is it 12? Dang. So the magic is going to happen next time. I can't believe you guys want to go because I'm willing to stay for yet another hour. And I have one more piece of paper. I could talk about this all day. Okay, so we'll pick it up from there next time, probably even start from the beginning next time. Get your web work finished, have a wonderful weekend, blah, 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 blah. You too, you guys at home? You're probably gone already because you can sneak out without me seeing you.
Thank you.
Questions? I'm gonna shut her down.
Thank you. Have a good one.
All right, here we go. Hit the old stop share button.